Okay, so since there's no more questions about the midterm, I'm guessing. No? Okay, so let's quickly review what we did last time, which are antiderivatives. And we say a function, capital F of x, is an antiderivative of another function, little f of x. And unfortunately, sometimes my capital F's look like my little f, so I'll try not to have that happen. So capital F of x is an antiderivative of little f of x if when I take the derivative of capital F, f prime, capital F prime, I get little f. So in other words, it's a function whose derivative is little f of x. Okay, so why are we doing this? Well, we might know, for instance, how fast something is changing. This happens frequently in physics, where you might know something about the rate at which something is changing. And we say, okay, I can measure the rate at which something is changing. Can you tell me about the original function, like position? Say I tell you something about velocity. Can you tell me something about position? Well, the idea is the velocity is the derivative of some function. And roughly speaking, there's what we have over here is if I know the derivative of the function y is some function little f of x, and I know what y is at some point, and we usually call this an initial condition, I can find the unique y that satisfies these two conditions. This is an initial value problem. So, for instance, if I know the velocity and I know where I am, say, at time 0, I can figure out where I am at any given time. Because once I have velocity, what do I know about the relationship between velocity and position? Well, the derivative of position is velocity. So the antiderivative of velocity is position. But you have to be a little bit careful here. What do we know? We know that two antiderivatives, because antiderivatives aren't unique, because I can always add constants, but in fact, if I have any two antiderivatives, they only differ by a constant. So coming back over here. So basically, if I know how fast if I know my velocity, I can find position up to some constant. That's why I need to have this initial condition. And so what it says is that my function y, if I have this relationship, is the antiderivative of f, which is some function, capital F plus an arbitrary constant. And then I just have to find what that arbitrary constant is, and then I use my initial conditions here to solve for that arbitrary constant. I also have some notation over there where I have this big line here. Think of this should look like a long S stretched out, is the way to think of it. This stands for the indefinite integral, and we're going to talk more about what integrals are. We're going to talk about definite integrals in I think, maybe Monday, or if not Monday, Wednesday. So the indefinite integral of fx dx is just another way of saying the antiderivative of f of x, or I really should say the general antiderivative, because, again, how do I find all antiderivatives? Is I find one, and I just add a constant. Now, antiderivatives are, of course, related to derivatives, and we have all these rules for derivatives. So we know that their rules for derivatives become rules for antiderivatives. With a star here, mean be careful. It's not as simple as it sometimes as you might think. I will say that once you know a few basic things about derivatives, you know the product rule, you know the chain rule, and you know the derivative of some functions. The trigonometric functions, powers of x, the log and the exponential function, which you'll learn about next quarter. Once you know those, it's pretty much a piece of cake to take the derivative of any function. But taking the antiderivative, that's an art form. It is hard to learn to master antiderivatives, because simple things that you think should work are almost always wrong. And as a general rule, if you're not sure whether or not you're allowed to do something, don't do it. You're probably going to get in trouble. So if in doubt, don't with antiderivatives. But what are some things that do work? If I have two functions added together, I want to find the antiderivative of them. I just find the antiderivative of each one separately and add the two together. If I have a constant times a function, I want to find the antiderivative of that. It's just the constant times the antiderivative of the function. And then some antiderivatives of simple functions. If I have x to the power of a, then the antiderivative of that is 1 over a plus 1, x to the a plus 1. Again, this is if a is not negative 1. And you'll learn about what happens when a is negative 1. When a is negative 1, it kind of wants to be a constant. So it picks the function which is trying really hard to be a constant as x goes off to infinity, but it's not quite a constant. And you'll learn about that function next quarter. The antiderivative of sine is cosine. The antiderivative of cosine is negative sine. So, wait a second. Did I get the signs wrong? Let's see. The derivative of sine. Yeah, I got the signs wrong. Okay. Make sure you get your signs right. It's really easy to confuse them because the signs change. So the antiderivative of sine is negative cosine. The antiderivative of cosine is positive sine. It's very easy for me to fix on my whiteboard here. How do you check if you're right or not? Well, it's very easy to check if you have the right answer. You just take the derivative. What is the derivative of sine? Cosine. So yes, now it's right. The antiderivative of cosine is, in fact, sine. What's the derivative of negative cosine? Well, it would be negative, is a constant, times the derivative of cosine, which is negative sine, which is negative sine, but two negatives make a positive, so it's just sine. Okay. The antiderivative of secant squared is tangent. The antiderivative of secant tangent is secant. The antiderivative of 1 over 1 plus x squared is arctangent. This is a good function to know, by the way. The derivative of arctangent is 1 over 1 plus x squared. All right. So that is what we talked about last time. Let's see. Should we try out a problem? Okay, so suppose I ask you the following question. Or I tell you the following question. Suppose I know that my acceleration at time t is 2 plus sine t. And I know something about what's happening at time 0. I know my velocity at time 0 is 1. And I know my position at time 0, which we use s, is 3. So I know these two facts. And I ask you the following question. What is my position at an arbitrary time t? Okay. Well, we think about it. Okay, is I have my acceleration at an arbitrary time t, and I just have to start thinking about how everything is related to one another. What's the relationship between acceleration and velocity? Yeah, the derivative of velocity is acceleration, or if we just go backwards, the antiderivative of acceleration is velocity. So that tells me that my velocity function is the antiderivative of 2 plus sine t dt. Or I should say it is a antiderivative, to emphasize that there's not just one. Okay, again, I can break this up. So this is 2 times the integral of dt plus the integral of sine t dt. And this is my rule of saying if I have two functions added together, I can just break it up over addition, and the 2 is a constant. It comes out in front. Now, eventually, after you practice this for a while, you're going to skip a lot of these intermediate steps, which is good. You should get to that point. But at the beginning, it's good to go through it step by step. Okay, so we get that the integral of dt, well, the integral of 1 is simply t. And the integral of sine t is, now that we fixed it, negative cosine t. And then finally, plus c. Now, let me just point out something here. Here we talked about integrals with x. And here we did integrals with t. Is there any difference? Yes, the x became a t. But besides that, it's no different. Don't be intimidated by these variable names. If I could put thetas or w's or y's, it doesn't matter. It's always the same tools, always the same steps. How do you find c? Well, yeah, we plug in what we know, which we know something at 0. So in particular, we know that v of 0, well, according to this, it's 2 times 0 minus cosine of 0 plus c. Of course, 2 times 0 is 0. So this is negative 1 plus c. And that should equal positive 1. So what can we conclude about c? C is 2. OK, so now I had my acceleration. And I took my acceleration plus this initial condition about velocity to find that velocity at time t is 2t minus cosine of t plus 2. What's my next step? Yeah, now my next step is I really want to find s. And so I say, OK, I'm going to bootstrap my way up, keep going up. And I say, well, I knew that when I took the derivative of acceleration, I took the derivative of velocity, I got acceleration. And so going backwards is the antiderivative. It's the same thing. The derivative of your position is your velocity. So the antiderivative of your velocity is position. So we have that. Our position is some antiderivative. So I'm going to replace what v of t is, because we have it over there. 2t minus cosine of t plus 2 dt. And again, I can break this up. So 2, the integral of t dt, minus the integral of cosine of t dt, plus 2, the integral of dt. And we just go through each one. What's the integral of t? So the integral of t, for instance, we use this rule. If I ever have something to a power, like x to the a dx, or t to the a dt, whatever it is, I add 1 to the power, and I divide by that new power. So add 1 to the t, this is t to the 1, so it becomes t squared, and I divide by 2. The integral of cosine, because we now fixed it up here, is sine. And the integral of dt we already did. So this, and then of course there's another constant. I'll use d just to say it's a different constant than c, which we used before. So this is t squared minus sine of t plus 2t plus d. And now we do the same thing we did before, where we used our initial condition. So s of 0 is 0 minus 0, sine of 0, plus 2 times 0 plus d, which should equal 3 according to our initial conditions. So I just plug 0 into here. This is our s of t. And everything became 0 except, of course, the constant, because it's just a constant all the time. And so therefore, I can conclude that the position function looks like t squared minus sine t plus 2t plus 3. So here's an example of how we might use antiderivatives. By using antiderivatives, we were able to start with our acceleration plus a little bit of information about our velocity and our position, just a little tiny bit, just a hint, and recover our position function. OK, so there's an example of how you might do an initial value problem. OK, so let's move on now. And I'll just let you know that Chapter 5 and Chapter 6, you are going to get a lot of practice doing this kind of stuff. So don't feel bad if you haven't mastered it yet. By the end of the quarter, you'll be much better at it. So let's go back, way, way back to the first day of class. Back when we were innocent. We still thought Professor Butler was a nice guy back then. That was before the first midterm. And during that first lecture, we talked about that there's really two things we're going to be talking about this quarter. Differential calculus, which asks the question, how fast is something changing? And now the other part of the quarter is what we start today, called integral calculus. Now this integral, by the way, is the same integral that we saw in the word indefinite integral. And remember, this was the question. This is, well, ask this kind of question. What is the total? Well, total what? Well, it depends on the question. We might be total area, total volume, total distance. It can be anything. If you're just asking for what is the total of something, or how much is there, that's the kind of question that we're going to try to answer with integral calculus. So let's start with a very simple example. We're just going to focus on area. And so right now we're going to focus on how much area is there. But the same principles we're going to find for this question are going to apply to questions in general. So if you also remember on the first day of class, excuse me, we talked about how, for us, we love flat things. So let's start off with a nice flat area. Sometimes we can do that. Suppose I have this curve y equals x, and I asked you, what is the area under this curve between, say, A and B? How much area is there? Now, hopefully, we can answer this one. So any ideas how to find it? Well, let me just give you, perhaps here's one way we could go about it. One way I could do it is I could say, well, let me think of this as the area from 0 up to b. But then I took too much, because I really just wanted the area from a to b. So what I'll do is I'll subtract off the little extra that I figured in before. Would you agree that these are the same? Essentially, I'm just rearranging areas. Well, I think they're the same, so I'm going to keep going. Now, what kind of shape is this? It's a triangle, yeah. So this length here is simply distance from 0 to b, which is b. And this length here, well, I'm on the curve y equals x. So that also is length b. So what's this area? Well, 1/2 base height. In this case, b times b. Come over here. This is a. This is a. And so the area, it's a triangle. Again, 1/2 base times height, which is a times a. So the total area is 1/2 b squared minus 1/2 a squared. All right. So we can do it for this nice picture. And we can do it because, what can we say about this line y equals x? It's flat. We love flat things. Except tires. We don't love flat tires. But most of everything else, we love flat things. Because that's what we understand. Intuitively, we understand what's happening when things are flat. We love triangles. We love rectangles. But now, I might ask you a different question. Suppose instead of y equals x, I give you something that's not flat. Y equals x squared. And I ask you, what is the area between 1 and 4? Okay. By the end of today, hopefully we can answer this question. All right. So if we think back what we did when we were asking about differential calculus, we said, well, we know the rate of change of a line. That's easy. So to find the rate of the change of a function, I'll try to make it look like a line. Okay. So let's try to apply the same kind of thing here. What's the easiest shape to find the area of? A square, or more generally, a rectangle. So we're going to say, well, what I'm going to do is I'm going to use my knowledge about rectangles, my infinite, deep, limitless knowledge about the area of rectangles, because those are easy. And I'm going to use that to try to figure out the area of that shape there. Now, at first, it seems kind of weird to ask such a question because it doesn't look like a rectangle. That's okay. We're going to make it look like a rectangle. So before we get to this specific question, let's sort of step back and look at a general question. So we have y is our function of x. And again, I want to go between a and b, and I'm looking for the area. So how do we go about this? Our idea now is the following. We're going to chop this into very tiny strips. And let's just say there are n of them. Now, my picture here, I drew them so they were roughly equally spaced. They don't have to be the same size. They can be whatever you want. So, for instance, I could have done the following. I could have chopped it up kind of in some weird fashion like this. But usually, it's very easy to think about them all being roughly equally sized. OK, so we're chopping into n strips. And if you look at every strip, let's suppose here, this is my ith strip. Let's focus on this for a second. Well, that strip looks almost rectangularish. And in fact, if we sort of squint and ignore the top here where it's kind of going like this, we can say, well, roughly, mostly it's just a rectangle with a little bit of air at the very top. So I can get a good estimate for what the area of this little piece is. So how do I find the area of a rectangle? Well, length times width. Now the width is basically, let's just say this is the bottom part, is we'll call it the width. And that's roughly delta xi is what we'll call it. This is the width at the bottom. So I look at the ice strip, and it has some width. Let's suppose we just call it delta xi, the width of the ice strip. And what's the height? Well, the height is basically going to be up here somewhere. Of course, it's not the same, because my function is not constant. It's changing. So what do? Well, what I do is I just pick any arbitrary point. Let's call this point. This is Ci is some point in the ith interval here. And what I'm going to do is I'm going to plug it into my function. When I plug it into my function, I get a value. And that value, if I think about it, I can treat it like the height of my rectangle that I want. Because roughly that is the right height of the rectangle, give or take a little tiny error. So this length here, which is the function evaluated at Ci, this is the height of the, what I'll call the ice strip. Or really, I should say this is the height I'm going to use to approximate the strip. OK, so I have the width, I have a height, and now it's very easy for me to talk about the area of the ice strip. Namely, it's approximately the height, f of Ci, times the width, delta xi. So right now we're all doing very symbolic things. We'll get into more concrete examples here in a second. Now that's just the area of one little piece. So what do I do now? Well, I do the exact same thing for every single one of them. So here our idea is we're going to chop things up into little tiny pieces. And for each little tiny piece, we have a pretty good approximation. That's really what we're doing, is we're saying for each tiny piece, we can get a pretty good handle on what it should be. It should be approximately the delta xi, the width at the bottom, times f of Ci, where Ci is somewhere in the ith interval. So I have a good approximation for each one. And then what I do is I just add them all together, and that should give me a good approximation for the total area. So the total area, well, that's going to be approximately, I look at the first interval. So this is the first strip, our first interval, whatever you want to call it. Plus, I look at the second interval. Our second strip. And I just keep doing that all the way until I get to the very last one. This board really wants to shake today. OK. This is the nth strip, or the last strip. Maybe I should use a different marker. And that's our idea. Now this here has a name. This is called a Riemann sum. And Riemann was a mathematician. Very smart guy. You can read a little bit about him in the next section, 5.2. OK. Now, we're going to simplify things. One of the things we're going to simplify is this allows us for any way we subdivide. We're going to simplify things and say we're going to allow for pretty much just two kinds of cases, or three, depending upon how you do it. So there's something we're going to do. We're going to do what are called the right-hand sums and left-hand sums. There's also something called midpoint sums, but I don't think we'll go into those. And what is the idea? Well, the idea here is we chop up the interval from A to B into equally sized strips. Now, when I talk about the size here, I mean the bottom. So in other words, it really does kind of match what happens in this picture, where every single width is the same. So I'm going to chop it up so all the widths are the same at the bottom. So what does that mean? That means I don't have a delta x1 or delta x2, delta x1. I just have a single delta x. It's all the same. So what is my width, delta x? Well, what's the total distance from A to B? For instance, if I go from 1 to 4, how far do I go? If I go from 1 to 4, I go 3. And the way you find it is you just take the high minus the low. So the width will be b minus a, the distance, divided by how many pieces you chop it up into. B minus a over n. Now that's just saying how we split up the interval. So what's the right-hand sum? The right-hand sum says you always choose ci on the right side of your interval. The left-hand sum says you choose the point ci on the left. Now what is ci? If you come back over here, remember that we're chopping up into our interval here. Ci is the point on the interval. So the right-hand sum says, just make it easy on yourself. Don't bother trying to pick an arbitrary point. Just always take the one on the right hand of the interval. The left-hand sum says, no, just always take this one over here, the one on the left end of the interval. So let's do an example here where we were trying to find the area between 1 and 4. Let's do some very simple things. Let's just do, say, n equals 3. So if I chop n equals 3, so I'm chopping 1 to 4 up into 3 pieces. How wide will each piece be? 1, because I say, well, I take 4 minus 1 and divide by 3. So fortunately for me, I planned ahead this time so that I got nice numbers. So I'm chopping this graph, y equals x squared, into 3 pieces. I'm going to try to approximate each little piece. So the right-hand sum, which we use an r to denote right-hand sum, and a 3, the 3 just denotes how many pieces we subdivide up into. So the right-hand sum, where I divide y equals x squared between 1 and 4 into 3 intervals, will be, well, it's going to be, just go through each single interval here. So here, at what point will I choose between 1 and 2? I'll choose 2. I'll choose 2 because it's on the right-hand side. So it's going to be, well, let me just write it out. F of 2 times 1, which is my delta x, plus, which point will I choose from 2 to 3? 3. F of 3 times 1, which is my delta x. And finally, from 3 to 4, I'll choose 4. F of 4 times 1, which is 2 squared plus 3 squared plus 4 squared. And then we add all these together, we get 29. Now what if I did L of 3? Well, we just basically do the same thing. We're going to go through for each one of these intervals. So from 1 to 2, which one is on the left? Or where is the left? It's at 1. So for the first strip, I plug 1 in times my delta x. For the second strip, what do I plug in? 2, because 2 is on the left-hand side. So f of 2 times 1. And for the third strip, plug in 3. So f of 3 times 1. So this is 1 squared plus 2 squared plus 3 squared. And if we add all these together, we get 14. So here we have 2 approximations. And of course, they're not the same. Let's see what we can say about these approximations. For instance, L of 3. Is that going to be too small or too big? Too small. Now let's think about why. What's happening with L of 3? Well, L of 3, let's see. I think we have blue somewhere. Let me grab the blue one really quick. L of 3 says you always take the left endpoint. So here, it's the left endpoint. when I plug in 1. So for the interval from 1 to 2, I'm using this rectangle here. I'm saying that this area, really I'm approximating using this rectangle. And you notice that the rectangle I have is smaller than the area I want. From 2 to 3, same thing. I'm using this rectangle here to approximate area. But you'll notice again, the actual area I want is bigger. And finally, from 3 to 4, I'm using this rectangle to approximate the area. So that for when we did the left-hand sum, we were always underestimating what the area should be. And so, of course, the total would be an underestimate. What if we're looking at the right-hand sum? Is this an underestimate or an overestimate? Yeah, it's an overestimate. Why? Well, because, for instance, from 1 to 2, I'm using this to help determine my height. So for that, I'm using this interval here. And you'll see that the area now that I'm using for the rectangle is actually bigger than the area I'm looking for. And from 2 to 3, my rectangle is now this rectangle here. So again, my rectangle is bigger than the area I want, and again, from 3 to 4. So we actually have a nice observation here. Let me write it down. What property of x squared caused L to be an underestimate and R to be an overestimate? Well, if you think about it, what happened was if I look at any strip, where was the low point? The lowest point was on the left-hand side. And where was the highest point? It was on the right-hand side. So what kind of function, when I go from left to right, I'm getting bigger? It rhymes with schmincreasing. Wait, no, schmincreasing. How's that? What rhymes with schmincreasing? Right, increasing. Good. Increasing rhymes with schmincreasing. Okay, so the hint works. Because as I go from left to right, I'm going up higher and higher. So that the problem here is I knew the left point would always be under. Because as I go from left to right, my function is going up. So the left was kind of too low. And I knew my right, for the same reason, would be too high. So we have this fact. If f of x is increasing from a to b, and this is a general fact. It's very easy to see. It's the same intuition we have there. Then we have that the left-hand sum, if I divide it into n intervals, n is arbitrary, is going to underestimate the area. And that the right-hand sum is going to overestimate the area. Similarly, if I have a function which is decreasing from a to b, well, now what's going to happen? Now which estimate is going to be an underestimate? The Rn is going to be an underestimate. So I'm going to use a capital A. And the Ln is going to be an overestimate. And just think of the picture. Just think of, here's one strip, and if my function is going down. The Ln now is the highest rectangle that would make sense. And so the Ln is going to overshoot what the actual area should be. And the Rn now is going to be the lowest rectangle, which makes sense. It's going to undershoot the area. Okay. Of course, these are all approximations here. We really don't want approximations. We really want to nail it down. All right. Well, so let's come back up and talk some more about sums. First off, it gets kind of annoying to have to keep writing this out in really long notation. So let's see if we can come up with a better notation. And there is. And the idea is we're adding up a lot of things which all essentially look the same. So we came up with a nice way to represent that situation. And so we're going to use the following notation. This is the Greek letter sigma. And when you see the Greek letter sigma, what letter does it start with? Well, it starts with the letter S. And you say S is for sum. So when you see the sigma, this capital sigma, you think, okay, that represents a sum. So here, in all its glory, is something you might see. Sum j equals m to n of a sub j. Now let me just talk about what everything is. J, this is called the index variable. Or, if you like, it's also called the dummy variable. And essentially, it's just helping you keep track of where you are. M is where you start the sum. N is where you end the sum. And AJ is what you sum. And usually it depends on J. If it doesn't depend on J, it's not a very interesting problem. So this says, this notation you would read the sum from J equals M to N of AJ. And what does it mean? This is equal to, we write AM, and then we just write the next term, which would be one more, AM plus 1. And we write the next term, AM plus 2. And we just keep doing this all the way up until we get to the last term, which will be AN. So this is just a shorthand notation that we have. So for instance, the Riemann sum here, what does it look like? So Riemann sum looks like a sum, let's say, J equals 1 to N. So here, what am I summing over? I'm summing over the strips. And then I have to sum the area of each strip. So the area of the jth strip, well, f of Cj times delta xj. This is just a nice shorthand notation for what I have here. What about for right-hand sums and left-hand sums? Well, for a right-hand sum and left-hand sum, we essentially, these are special cases of Riemann sums, so they look like this. So we just have to sort of plug into the formula. So Rn, well, n is the number of strips. So again, we're going to sum over n strips. So it's the sum, J equals 1 to n, f of something, I'll go into that in a second, times delta x. And delta x now, there's no longer really depends on j. Delta x of j is always going to be the exact same thing, so we just call it simply delta x, where delta x is this v minus a over n. Now, what goes inside here is the tricky part. So if I think of what I'm doing, I have here a, here's b, and I divide it up equally into n strips. Each one has width delta x. So forth and so on. So suppose I want to find, this is my ith strip here. What is this coordinate? Where is it located? Well, let's think of it. I started here at A, and then I went delta x once. That's the end of the first strip. If I start at A and I go 2 delta x's, I get to the end of the second strip. If I start at A and I go 3 delta x's, I get to the end of the third strip. So if I start at A and go I delta x's, I get to this point on the ith strip. So I started at A, and I added delta x I times, so that the right endpoint is going to be A plus I. Oh, sorry. Should have done J, since we had our index here as J. So A plus J delta x. So this is just saying this is the right endpoint. All right, let me erase this. I'll just move it down. How about Ln? Well, again, we're going to sum from j equals 1 up to n. Function somewhere, delta x. Now, the difference between, of course, the right-hand sums and the left-hand sums is that the right-hand sums we want the right endpoint, the left-hand sums we want the left endpoint. So all we need to do is just tweak what's inside. So for instance, if I want to get to the very end here for the right hand, really for the left hand, I don't want to go quite so far. I want to go one less. So for instance, for the first strip, I don't even move at all. I just go for A. On the second strip, I go for this point here, which is A plus 1 delta. On the third strip, this strip, I go for this point here, which is A plus 2 deltas. And in general, for the jth strip, I'm going to go a plus j minus 1 delta x. Now, the book does something really cute and very clever, which it says, you know, this index is a dummy index, so I can just change the name. So we don't have to sum from j equals 1 to n. I can do a little trick and just relabel everything. And here's my trick. Let me just show it to you really quick. I'm going to let I be equal to, let's see, sorry. I'm going to let j be equal to I plus 1. So that if j equals 1, what should I be? I would be 0. So I don't start my sum at 1, I start my sum at 0. And if j is n, what should I be? N minus 1. So because it's a dummy variable, I can just, anything that involves the j, I can just tweak it, doing some very simple transformation here. So instead of going from 1 to n, I can sum from 0 to n minus 1. And now the trick here, of course, j equals I plus 1, or another way of saying this, j minus 1 equals I. So this becomes f of a plus I delta x delta x. So very similar. Essentially, they look the exact same thing. The only difference is one goes from, the right-hand sum goes from 1 to n. Left-hand sum goes from 0 to n minus 1. Now, the sums obey some nice properties. Let me just write some of these nice properties down, and we can use those. So, for instance, if I'm summing j equals m to n of aj plus bj, so I have these two things that I'm summing, what can I do? Well, I can sum from m up to n of aj, and then I can sum from m up to n of bj. So in other words, I can break sums up over addition. This should look very familiar. We've been doing this kind of things with derivatives and also with antiderivatives. Another thing I can do with sums is, of course, I can pull out a constant. So I have a constant times aj. The constant can come out in front. Now, this really should not be very surprising here. If you were to actually write it out, this says that if you have kam plus kam plus 1 up to kan, well, what's in common here? They all have k. OK, well, factor out the k. Kam plus am plus 1 plus an. And you say, well, what is that? Well, that's exactly this sum right here. So this is not profound. This basically says you can factor out things that are common. Similar thing, this is not profound at all. This just says I can rearrange the way I add numbers together. The fact that 1 plus 2 is 2 plus 1 is all that I need to use here. That order doesn't matter when I do addition. And of course, I can also do this trick here where I can reindex or change my dummy variables around. Now, we're going to need to know a few facts. Where can I put my few facts? I'll put my few facts over here. So here's some nice facts. Suppose I sum I equals 1 up to n of 1. What should we get? So I add 1 plus 1 plus 1 plus 1. At a total of n times, the total will be n. Sum I equals 1 to n of I squared. Now, what is this? This is 1. Oh, sorry, let's just do I. 1 plus 2 plus 3, all the way up to plus n. Does anybody know this one? This is n times n plus 1 over 2. Or, if you like, this is 1/2 n squared plus 1/2 n. OK. And this is the one that we really will need. Sum I equals 1 to n of I squared, which is 1 squared plus 2 squared plus 3 squared up to n squared. Now, if you know this one, I'm very impressed. This is n times n plus 1 times 2n plus 1, all divided by 6, which is equal to, if you multiply it all out, and if I had more time, I would actually do that step by step. This is equal to 1/3 n cubed plus 1/2 n squared plus 1/6 times n. OK, let me just mention, this is a fun historical fact, probably not true, but we like to tell it like it is true. How can you prove this really quickly? Well, 1 plus 2 plus 3 all the way up to plus n is the same as saying n plus n minus 1 plus n minus 2 all the way to 1. So I just write it backwards underneath. What's n plus 1? Oh, n plus 1. What's n minus 1 plus 2? Oh, n plus 1. What's n minus 2 plus 3? N plus 1. What's n plus 1? N plus 1. In fact, you notice that I always got n plus 1. How many n plus 1s are there? There's n of them. So I get n times n plus 1. But of course, that's twice what I wanted. So it's n times n plus 1 divided by 2. This was done by a young kid who was really annoyed in class one day. I'll probably tell you the story next time. OK, so don't forget, midterm on Friday. My office hour is on Friday morning. I'll extend a ½ hour each direction. So 7 to 9:30 on Friday morning, I'll be in my office if you have any questions.